Okay, everyone, this is a discrete mathematics class, and today we want to talk about the relation and see some properties of the relation. If you remember, last week we talked about the set. Set is a collection of the object which has no repetition and order of the all element written in the set has no order. Let us write the two sets. Assume A is this set. If I can write it, yes, I did. For example, A, B, and C, one of the set. I want to write one another set, B. Let us write something like 1 and 2. Okay, so these are two sets. I want to make it the cross product of these two sets, A cross B. We have an A1, we have an A2, B1, B2, C1, and C2. So we have a set A and set B. We can define the cross product of AB, which has a 6 element here. Now think about the subset of A cross B. How many subsets we can define? Since we have a 6 element in A cross B, you can define the 2 to power 6 different subset of A cross B. Okay, I want to pick up one subset. This is one subset. For example, A2, B1, C1, and C2. This set is a subset of A cross B. Since it's a subset of A cross B, we call it a relation and we show it by R. So what's the relation? Relation is a subset of Cartesian product. Any subset of Cartesian product, we call it relation. So if I gave the one set and said that, okay, is that relation or not? Like this one. Pay attention. A2, B1. Let me show it by something like maybe R1. So is R1 a relation or not? To answer about it, is that relation or not, you have to check. Is R1 subset of A cross B? If answer is yes, therefore R1 is relation. If answer is no, R1 is not relation. That's much easier. Is that clear? Today we want to talk about this issue, relation. So as you see, since R is a subset of A cross B, means element in A cross B, all of them, if you look at it, all of the element in A cross B, all of them are written as pair. Look at it. This is pair, pair, pair. All of them are pair, such that first element always comes from first set, and second element always comes from second set. So if you come in R, if you pick up any element, first of them comes from first set, second element of that pair, means component, comes from the second set. Means that first one comes from A, second one comes from B, because we have A cross B. Okay, let us right. So if you have two sets, let us call it A and B. You have two sets. If you make the Cartesian product of these two sets, A cross B, any subset of A cross B, we call it relation. Any subset. So how many different subsets we can have it? You know it. How many elements do we have in A times how many elements do we have in B? Multiply them. 2 to the power number of the element in A and B. Call it that much subset. Therefore, all of them are relation. So if first set is A and second set is B, relation is, for example, if you pick up the A, B in relation, if this is an element in relation, means This one comes from A, and second one comes from B, because first one is A and second one is B. At that time, we call it A and B are related. A and B are related. Like a previous example, look at it. Here we said that B and 1 are related. How we say that B is related to 1. B is related to 1. And also here we can talk about the C and 2. We said that C is related to 2 because those are elementary relation. How we can show them? We can show it in two ways. We said that AB is an element of R, or we said that A is related to B. So let me go to the previous example and talk about the disconjugate relation. For example, in this example, we said that A2 is an element of relation. And also we can write it in this way. A is related to 2. Both of them have the same meaning, because A and 2 is here. Look at it. This is A2. So we can write it in two ways. Sorry, first one is A. So you see, topic is really easy topic. Talking about the example, we have many students in the first set: Alex, B, Kat, Don, Eddie, Fiona. And the second set is a subject. Let us call it course. And these are code of the courses: IP1, FP1, AF2. These are code of the course. For example, like our course, we call it Mat2033, means discrete mathematics. That's a code, just represent this course. R is a set which shows that Alex take to the IP1. This relation means the student take to the course or pass to that course. Alex IP1, Alex AF2, B AF2, Cat AF2, Cat IP1, Done AF2, Done IP1, Fiona IP1, Eddie IP1, Fiona FP1. Sorry, last one please correct it. This is not the FP1. This is not FP2. This is FP1. Correct it, please. Okay. So, question is our relation? How we can understand is that relation or not? To answer about the relation, check. Is that A cross B? What's the A? First set is A. B, second set is B. Now, is that subset of A cross B? Just imagine about it. Cartesian product of set A and Cartesian product of set B. Just imagine about it and then answer it. Is R subset of A cross B? Answer is yes. Since R is a subset of A cross B, we call it R is a relation. Therefore, R is a relation. In this example, pay attention. Since the relation at the end, we know that this is a set. Look at it. For example, this element in a set. B and AF2. It does not matter where you want to write it. You want to write it in a first element. You can write it in between the first and second. You can write it, shift it, and put it in anywhere. Maybe you can put it here. It's not matter, because at the end this is a set. So order between pairs is not important. But thinking about any element inside, just let us talking about the B AF2. Look at it. B is a student take AF2, pass the discourse. Can we write it in this way? I said that AF2 and B. Answer is no, because here relation said that student passed the discourse. So this is student passed the discourse. If you write it in this way, AF2 and B means that course passed this student. Has no meaning. So order inside of the element of relation is important. You cannot do it easily. Let us see the graph of this relation. So this is a relation that we have. We have a two set. First set is a set of students. Second one is a set of courses. Look at it. Alex, IP1. So Alex take these courses. So put the arrow. From Alex goes to IP1. Go to the second element. Alex AF2. Alex AF2. Go to the next one. B AF2. B AF2. Do all of them, you see the graph. So this is one another way to show the relation. So if you have a relation up to here, we saw that we can show it in two ways. One of them is showing as a set, the other one is showing as a graph. So both of them have the same information. Let me ask one question in high school level. As this graph, is that function? Answer is no. Why it's no? Because here, to be a function, any element in domain, first one we call it domain, we'll talk about it later, or set of input. Any element must have exactly one output. Look at the Alex has two outputs, and also cat has a two output, Donna as well, Fiona as well. So impossible to be a function. So at the moment, just note that function is a one special case of relation. Function is a special case of the relation that we will talk about the function later on. So note that it's not a function. If you have a one set, let us write it in an easy way. With two elements. Make a cross product with itself. How many elements do we have in A cross A? 4 elements. Let me write them. So A cross A is AA, AB, BA, and BB. This is A with 2 elements. A cross A had 4 elements. Now thinking, how many different relations we can define on a set A? To find the relation, you have to find the Cartesian product and pick up one subset. How many subsets you can take it? 2 to the power 4. So in a set A, if you have 2 elements, we have this much relation that you can define on it. Let me say that if in an A we have 3 elements, how many relations you can define? 2 to the power. At first you have to define the Cartesian product. How many elements do we have in Cartesian product? 3 square. Means 9. How many relations we can define? 2 to the power 9. Then instead of 9, I want to write it 3 to the power 2. So if in A we have 10 elements, how many relations you can define? 2 to the power 100. You can write it as n square. So in general, if in a set we have an n element, how many relations we can define? 2 to the power n square. So if you have one set which has an n element, how many different relations we can define on that set? This is the answer, 2 to the power n square. Let me erase it. So we make the A cross A. Since in a set A we have an n element, in A cross A we have an n square number of elements. To find this relation means how many subsets you can pick up it. Is 2 to the power. So we can define this much different relation on a one set which has an n element. So since we have a really huge number of the relation, just imagine about this one. In a one set, if you have a 5 element, in A cross A, we will have 25 elements. How many relation you can define on it? Number of relation is 2 to the power 25. It's really huge number. It's really huge number. Just if you have in one set, you have just 5 elements, you can define this much different relation. Since it's a really huge and big and wide topic in relation, we want to focus about some specific relation, which we call it equivalence relation. Equivalence relation is one of the most useful relation, and it's an important one. That today we want to talk about the equivalence relation. At first, let us see that how we can show relation. To show one relation, we have 3 different ways. One of them, which is the easiest one, show as a set. That we had a couple of the examples. Show it as a set. The other one is using the graph that we showed. This one an example the student after the course. And last one is a method that we call it matrix way. So if you have one relation, you can show it in 3 different ways. Using as a set, showing as a graph, showing as a matrix. So if you show it by graph, we call it directed graph. If you use it a matrix, we call it relation matrix. Relation matrix. Let us see that how it's working. This one. Let me call it by R. It's not matter which name label you want to put them. This is a R. This is a one set, which is defined on the set A. First one, is this set is R relation? To answer about the is R relation or not, you have to check, is R subset of A cross A? We have an A, is written 1, 2, 3, 4, 5. We just make a Cartesian with itself and check, is R subset of A cross A? In this question, answer is yes. Therefore, R is a relation. So one of the way to show that the relation is just elements of that relation. Done. Now about the graph. How we can show the directed graph? To show the directed graph, pay attention. Always we have to use the set A. How many elements do we have? For each element, put 1 dot and label them. 1, 2, 3, 4, and 5. It's not matter where you want to put these dots. Just put dots in somewhere. After that, come back to the relation. 1 and 2 means for each element of relation, use 1 arrow. This one is started point, initial point. This point is terminal point, end point. So put the arrow from 1 goes to 2. Next one, 1 goes to 3. Next one, 1 goes to 4. Next one, 2 goes to 3. 4 goes to 4. To show that the 4 goes to 4, look at it. How we can put the arrow started from the 1 point and end exactly in the same point. For that reason, we are using 1 circle. We call it loop. Look at it. 4 goes to 4. And last one, 4 goes to 2. This is a graph. This is a graph of the relation. We call it directed graph. Both relation as a set or using the directed graph, both have the same information. And both of them shows that, okay, this is a relation on a set A. Pay attention here, we have a one number 5. We didn't use it actually in a graph. But still you have to write it. You have to show it. Always you have to do show it. So in A, if you have an 5 element, at first you have to show all of them, even there is no any arrow about that element. And next way is using the relation matrix. What's a relation matrix? At first, check the set A. How many elements we have here? 5. Draw 5 by 5 matrix. 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5. Now start to label them. Each rows, use the element of set A to label them rows 1, 2, 3, 4, and 5. Same thing for the columns 1, 2, 3, 4, and 5. Now come back. Look at it. Here we have a 1 and 2. First one is written in a row. Second one is written in a column. So 1 and 2, where is that? It's here. So put 1 if there is such an element. Next one is 1, 3, we have it. 1, 4, we have it. 2, 3, we have it. 4, 4, we have it. And 4, 2, we have it. And if we don't have the rest part, put the rest, all of them 0. We call it a relation matrix. So there is a 3-way to show one relation, using as a set, using as a graph, using as a relation matrix. All of them have the same information. I think topic is not really a hard topic. Let us erase it if you have no question. Do you have any question regarding the relation? Okay, let us erase this page. This is a graph, and this is a map. Now let us have a different example. Look at this relation, or said that A and B are related such that A and B, both of them are natural numbers, and B is equal A plus 1. Let us list few elements of this relation. We have 1 and 2. Check it. First element 1 and 2, both of them comes from natural number. And B is equal, second component is equal first component plus 1. We have a 2 and 3. We have a 3 and 4. 4 and 5. Blah, blah, blah. Now check. Is our relation, how we can understand is our relation or not? We have to check that is that subset of A cross A? In this question, what's the A? A is a natural number here. So, talking about the relation, you have to say that is our subset of natural number cross natural number? Say it. Answer is yes. Therefore, this is a relation. Since this is a relation, how is the graph and how is the directed graph and how it's relation matrix. You have to list all elements of the natural number. 1, 2, 3, 4 up goes up to infinity. We know that 1 goes to 2, 2 goes to 3, 3 goes to 4, and etc. And about the matrix, how we can use the matrix? You have to draw the infinity by infinity matrix, because here set A is written as natural numbers. Since we cannot draw the infinity by infinity, we just show that some part of that matrix. We write it 1, 2, 3 goes up to infinity in the rows, and then in a column 1, 2, 3, 4, 5 goes up to infinity, and show that 1 is related to 2, 2 is related to 3, 3 is related to 4, 4 is related to 5, 5 is related to 6, blah blah blah. The rest, all of them are 0. So in a one set, if we have a 5 element in a set A, how many relation we can define on it? 2 to the power 25. That one is something like a more than 30 million relation. It's a really huge number of the relation. For that reason, we focus about some specific relation, which we call it equivalence relation. What's equivalence relation? Equivalence relation is a relation which it is reflexive, symmetric, and transitive. So any relation which be reflexive, symmetric, transitive, we call it that is equivalence relation. Okay, now let us see that what's the reflexive, what's the symmetric, and what's the transitive. To understand about the reflexive, at first you have to check your set A. Pick up any element in A. Do it for all of the element of A. Pick up any element of A. For example, A, this not capital one, element, small one, lowercase, and check, do we have a in a relation? If answer is yes, we have it for any selection element in your set A, therefore we call it that relation is reflexive. For example, this one. This is set A. 1, 2, 3. And I want to define relation R. This way. 1, 1, 1, 3, 2, 1, 3, 3, 2, 2. Let me write a different one. For that reason, I want to put the sub 1. R sub 1. R sub 2. Let me write a different one. Let me write a different one. Let me write a different one. One and 1, 2 and 3, 3 and 3, 2 and 2, 1 and 4. Now check about the first one. Is that reflexive? To understand about the reflexive on this set, this is set A, is R1 reflexive? Look at the set A. We need to check 1, 1, we need to check 2, 2, we need to check 3, 3. All of them must exist under the set. If all of them exist, we call it yes, that is relation. So in the first one, we have 1, 1, we have 2, 2, we have 3, 3. all of them. Therefore, yes, it is reflexive. R2, is that reflexive? Again, 1, 1, 2, 2, 3, 3. Yes, we have all of them. Therefore, it's reflexive. R3, we do not have a 1, 1. Therefore, it's not reflexive. R4, we do not have a 3, 3. So it's not reflexive. Now about the R5. Is that reflexive? We know that we have a 1, 1. We know that we have a 2, 2. We know that we have a 3, 3. But this is not reflexive. Why it's not reflexive? Because R5 is not a relation. Why it's not a relation? For example, look at this point, 1 and 4. Do we have a 4 here? No. Therefore, R5 is not a relation. Since it's not a relation, it's impossible to be a reflexive relation. So we don't talk about this kind of set. R5 is just one set, is not relation. So that's a topic talking about the reflexive. I think reflexive is one of the easiest elements and one of the easiest relation part. So how we can understand is that reflexive or not? You have to check your set A, and all the element in the set must be related to itself. At that time we call it okay, that is reflexive. Now check this one. Pay attention. R prime here that I wrote, it means just a different R. You can write it as R1. So just nothing. R. R is a one relation which has an element x and y. Both of them comes from natural number and x is less than equal y. Is that reflexive? Okay, we'll come back to the natural number. Natural numbers is a set of means 1, 2, 3, 4 up to infinity. Now, is R reflexive or not? Means, do we have a 1, 1? Yes, because 1 is less than equal 1. Do we have a 2, 2? Yes. 3, 3? Yes. 4, 4? Yes. But how we can answer it? To answer, you don't need to write just the element, just example. If you do it, here we have an infinity many number, how you can show them all of them one by one. For that reason, we pick up the one element in natural number. We said that. Let us take one element in natural number and check. Do we have that element related with itself in our relation? If answer is yes, therefore this relation is reflexive. So look at it, x, y is related if x is less than equal y. So a is related if a is less than equal a. Is a less than equal a? Yes. Therefore this one is reflexive. That is reflexive. Done. This is a way to prove that this relation is reflexive. And next one is talking about in a one set if you have 5 elements. How many relations we can define? How many relations we can define under that set? Number of relation is 2 to power 25, 2 power 5 square. Look at it here, we have a 5 number, therefore it's 5 square. This much different relation. How many of them are reflexive? We have this much different relation. How many of them are reflexive? That's a question. Let me make it a little easier. Just let us make it up to 3. Okay. How many relations we can define? 2 to power 9. This much. Different relation. How many of them are reflexive? At first, you have to write an A cross A. Let us write them. We have a 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, and 3, 3. We have this much element in A cross A. Pick up any subset. That is a relation. So if you pick up subset, that is definitely a relation. But we want to say that how many of them are reflexive? To be a reflexive in a relation, we need to see 1, 1, 2, 2, 3, 3. Okay, let us pick up 1, 1. Let me change the color. I want to use 1, 1. I wrote it. Use 2, 2 because I need it, because I'm trying to make it one relation which will be a reflexive, and also I need 3, 3. Now you can add anything that you want. Definitely the set that you have it will be reflexive because we have 1, 1, 2, 2, 3, 3. These are enough to say that this relation is reflexive. Okay, how many items you can add? How many possible selection you have to add it? Some people say that no, I don't want to add anything. So still R is relation. Someone said that no, I want to add just one element, maybe just this one. Still is a relation. Maybe someone said that no, I want to add the 2 elements, 1, 3, and 2, 3. Still is a relation. Reflexive. So how many possibility do we have to adding something here? 1 is a possible, 2, 3, 4, 5, and 6. Here we have a 6 element that you can pick up any subset of this element. How many possible subsets do we have if in a set we have a 6 element? 2 to power 6 different way. 2 to power 6, not 6 to power 2, Ali. So 2 to power 6 different way. 2 to power 6. So in a set, if you have a 3 element, 2 to power 9 is a number of different relations. 2 to power 6 is a number of reflexive relations. Now let us write it in general. In a set A, if we have n element, how many relations you can define? 2 to power n squared. How many of them are reflexive? 2 to power n squared minus n. Look at it here, we have 6 elements that we use 3 of them. Rest is 2 to power 6. So this much relation, this much reflexive relation. Reflexive relation. Let us erase this page and see the slide. In a set, if we have 5 elements, if in a set we have 5 elements, how many relations we can define? 2 to the power 25. How many of them are reflexive? 2 to the power 20. Means power 25 minus 5. Means n squared minus n that I wrote down the page. Now look at this set. In this example, set A is given integers. And we have 6 different relations. Which one is reflexive? About the first one. Is that reflexive? Means, do we have a AA in R? Answer is yes, we have it. So first one answer is yes. Second one, no, we don't have it. Third one, yes, we have it. Next one, yes, we have it. R5, no, we don't have it. R6, is R6 reflexive? For some element of A and B, yes. For some element, no. For example, in a set of integers, 1, 1, do we have it? Have it. 0, 0. Minus 1, minus 1. Minus 10, minus 10. Yes, we have them. But it's not meaning that those are reflexive because, for example, we do not have a 2, 2. Since we don't have a 2, 2, stop and say that this is not reflexive. Not just 2, 2. Maybe you can say that, okay, we do not have a 5, 5 as well. But since you found the one element which is not relative to itself, therefore that is not a relation. So R6 is not. Now, next part is talking about the symmetric, because at the first we said that we are talking about the some relation which we call it equivalence relation. What's equivalence relation? A relation which is reflexive. We learned about it. Next one, symmetric and transitive. Now we want to talk about the symmetric. What's the symmetric? Symmetric is if you have A, B in relation, then its reverse also must be exist. Pay attention, A and B must be different. Because if A and B are same, don't check that one. If you have an AB, then check the BA. Let me write it as something. This is the set A, 1, 2, and 3. I want to write some relations. Another one. Empty set, last one is empty set. Okay, let us check. Which one is symmetric? Let's start from the first one. Pay attention condition said that at first pick up, then check its opposite one. Okay. Don't check 1, 1 because we said that we need to see the opposite. They are different number. 2, 3. We have it. Do we have a 3, 2? Yes, we have them. So far, we have no problem. Go to the next one. 1, 2. Do we have a 2, 1? Yes, we have them. Can you see? All of the numbers has its reverse as one as well. 2, 3, we have a 3, 2. 1, 2, we have a 2, 1. So R1 is yes, it's symmetric. Go to R2. Pick up numbers that they are different. 1, 2. Do we have a 2, 1? Yes. 3, 2. Do we have a 2, 3? No. I said that since we have a 3, 2 in a relation, but we don't have a 2, 3, therefore this R2 is not symmetric. R3. 2, 3. Do we have a 3, 2? No, so it's not. Do you have any questions so far about the symmetric? I think no. Okay, no. R4. We have a 3, 2, and also we have a 2, 3. Good. R5. What do you think about the R5? Is that symmetric? Ali said yes. Taha Burak said no. I'm talking about the symmetric. Pay attention. Definition of symmetric is pick up A and B in a relation which they have a different number. 1 and 2, we don't need to check. 2 and 2, we don't need to check. Is there some number which their reverse does not exist? No. So that is symmetric. That is symmetric. Look at the R6. R6, is that symmetric? R6, is that symmetric? Answer is yes, it's symmetric. Because we do not have such a number, two different numbers like A, B exist, but B, A does not exist in this kind of relations. So R5 is yes symmetric, R6 also is yes symmetric. Let us see the graph of R1. 1, 2, 3. We have 1, 1. We have 2, 3. We have 1, 2. And also we have a 2, 1. To show 2, 1, you can use it two way. Look at it. 1, 2. You can show it in this way, and also you can show it in this way. So I want to use it this way. 1, 2, and 2, 1. And 3, 2. This is for R1. Let us check R2. I want to write it in R2 in the right side. 1, 2, 3. We have a 1, 2. We have a 2, 1. We have a 3, 2. And also we have a 1, 1. R1 is reflexive, symmetric. R2 is not. This is not. Check why R2 is not. Because, look at it. We have a one arrow which is just in one side. R1 is reflexive because all of the arrow, all of them are in both sided. So we can conclude that in a one graph, if you have just one-sided arrow, if you see one-sided arrow, impossible to be asymmetric. Now let us check with R5 now. Let us check with R5 now. Easily now you will understand why R5 and also R6, those are symmetric. This is a R5. Look at it. 1, 2, 3. That's a R5. Do we have any just one-sided arrow here? No. Therefore, it's symmetric. Now I want to draw to the R6. This is R6. This is R6. Let me just show it. Okay, this is R6. R6. Now, is that symmetric? To answer about the symmetric. To answer about the symmetric. Do we have any one-sided arrow here? Answer is no. Since we do not have just one-sided arrow, therefore it's symmetric. I know that we do not have an arrow, but if we have a one-sided arrow, if in a graph you saw one-sided arrow, definitely that is not symmetric. Otherwise, yes, it's symmetric. Let me talk about the matrix. Maybe that won't help you if still you have a problem about the symmetric. I want to show you R1 as a matrix. Let me finish the matrix. At that time, you will understand what's the meaning of symmetric. Look at it. This is the R1. We have 1, 2, 3 here, and 1, 2, 3 here. Now this matrix, we have a 1, 1, we have a 2, 3, we have a 1, 2, 2, 1, and also 3, 2. Is this matrix symmetric? Answer is yes, it's symmetric. Because look at the main diagonal. These are symmetric. And about the part that I didn't put them anything there, means all of them are 0. Look at them. Is that symmetric? Answer still is yes, symmetric. Now look at, for example, R2. Here I want to draw to the R2. One, two, three. 1, 2, 3. We have a 1, 2, we have a 2, 1, we have a 3, 2, we have a 1, 1. Is this matrix symmetric? Here's all of them are 0. No, it's not symmetric. Can you see? We have a 3, 2, but we do not have a 2, 3. Now let us talk about the R5. Let me erase some part. What's happened to Abrak? One, two, three. 1, 2, 3. I'm drawing R5. We have a 1, 1, we have a 2, 2. Rest, all of them are 0. Can you see? This one is still symmetric. And also about the R6. This is a R6. Look at to the right. Here, this is R6. All of them are 0. So we saw the definition of the symmetric. If we have AB in a relation such that A and B are not same, then you have to check the BA as well. For any selection of AB, we have all of the BA as well. At that time, we call it the symmetric. Like this one. This is a relation on a set A. AB are related. A and B are natural numbers such that summation is odd. Is that symmetric? We write that if we have an AB in relation, then we need to check BA. A and B are different. So since AB is in relation, means A plus B is odd number. Now, do we have a B? A in relation means how much is B plus A? Is that still odd? Yes, it's odd. Therefore, it's symmetric. Look at the matrix. We have a 1, 2, we have a 1, 4, we have a 2, 1, we have a 2, 3, blah, blah, blah. Look at this matrix. A symmetric matrix. And look at the graph. Do we have it in just one direction arrow? We do not have it. We do not have it. So this one is symmetric. By the way, this relation, is that reflexive? To be a reflexive, come to the natural number. Taha, you don't need to be sorry. We know that some student will have a maybe technical problem. If you've been disconnected, don't worry, we are video record after the class. After the class, you will have a chance to watch and listen to the topic. Anytime if you have any problem, you know that how you can contact. Just you can send me an email or you can call my office phone number. Don't worry about it. And don't be sorry. So don't be sorry. Okay, let us talk about the reflexive. Come to the natural number and think about it. Do we have a 1, 1? Do we have a 2, 2? Do we have a 3, 3? Do we have a 4, 4? All of them. Sorry, 2, 2. Oh, it's a 2, 2. 3, 3. 4, 4. And so on. If one of them, at least one of them, is not in the relation, therefore this is not reflexive. Look at it, 1, 1. Do we have a 1, 1? No, because summation is not odd. Therefore it's not reflexive, so you don't need to check the rest. Look at the matrix. To be a reflexive, main diagonal, all of them must be 1. This is a main diagonal. All of them must be 1. Is that really all of them 1? No, for example, look at the 1, 1. This is not 1, so you don't need to check rest. This is not reflexive. And about the graph, look at the graph. Is that reflexive? Means we have a 1, 1. Means all the number that you have it, all the elements that you have it, all of them must have a loop. Do we have a loop here? No. Therefore, in 1. Do we have a loop? No. Therefore, it's not reflexive. And also, it's not. We do not have a 2, 2. We do not have a 3, 3. If one of them has no loop, definitely stop and say that, okay, that is not reflexive. And last part, talking about the equivalence relation. At the first, I said that any relation which would be a reflexive, symmetric, transitive, we call it equivalence relation. Reflexive, symmetric, transitive. Reflexive, without, symmetric, without. Now it's the time to talk about the transitive. What's a transitive? Pay attention, if we have a AB in relation, and also we have a BC in relation, then you have to check AC in a relation. If we have a AB, BC, then check AC. At that time we call it, okay, that relation is transitive relation. In the other word, if you can go from A to C in 2 steps, means you can go A to C in 1 step as well. Look at it. We can go from A to C in 2 steps. Sorry. We can go A to C in 2 steps. And also we can go in 1 step as well. At that time we call it, okay, this one is transitive. Let us have a summary. Reflexive means For any element in your set A, we have a AA. For any element in your set, you have to check AA. Symmetric. If we have a AB, which they are not equal, then we have a BA. Symmetric. Symmetric. Pay attention about the antisymmetric. If we have an AB in a set, which they are not same, but we don't have a BA, means antisymmetric. The last one, transitive. If we have an AB and also we have a BC, but we do not have an AC. How we can check them? I want to talk on graph. If all elements have a loop, means all of them have a loops, we call it reflexive. About the symmetric, if you saw one directed arrow, definitely that is not symmetric. Antisymmetric, if you saw just one by both-sided arrow, definitely is not antisymmetric. It's not completely set that opposite of symmetric, it's antisymmetric. So in a graph, if you saw one-sided arrow, one direction, it's not symmetric. If you saw both-sided arrow, it's not antisymmetric. And about the transitive, we'll talk about the transitive later. An example. Let me just write it here. A, B, C. Look at it. A goes to B, B goes to C, and A goes to C. Look at this one. This is a case to say that this is a cycle. Look at it. It's something like a cycle. Tap, pop, pop. And compare with the transitive and this cycle. Just one of the arrow is reverse. In the other word, if you saw the one triangle back to back, arrows are back to back, but the other one is removed. It's not here. That is definitely, it's not transitive. So in a graph, if you saw one triangle which one side is removed and these two arrows are back to back, definitely that is not transitive. Okay. This is an example for reflexive. A divides B. A divides B. Therefore, B divides A as well. Any number can divide itself as well. Sorry. If A divides B, means any number can divide itself. Therefore, that one is reflexive. Means look for any element of your set A. Symmetric. If we have a AB and also BA, example, A is married to B, we can say that B is married to A as well. We have a both direction arrow. That's symmetric. A divides B. If A divides B, we cannot say that B also divides A. Or like this one, A is a parent of B. That one also is an example for antisymmetric. If A is a parent of B, B cannot be a parent of A as well. Antisymmetric means in a graph, if you saw all of them must be in one-sided. If you saw the both-sided arrow, if you saw the both-sided arrow in the graph, definitely that is not antisymmetric. And that's transitive. Means A is less than B. If A is less than B, B is less than C. Definitely A is less than C. Look at it. A goes to B, B goes to C, and A goes to C as well. Means from A to C, You can go in 2 steps, and also you can go in 1 step. Means transitive. Okay. We have a 1 set, 1, 2, 3, 4. Which one is a reflexive? Let me draw one table here. I want to write. It's really hard to draw it. Let me try to find some way to draw it easily. I want to try to use a ruler if I can take it. Okay, come up. It's not working there. It's really hard. Oh, let me just do it by your hand. Ruler also is really hard. Reflexive, symmetric, antisymmetric, and transitive. R1, R2, R3, R4, R5, R6. I want to add some things. R7, R8, I want to write R7. This is a R7. 1, 1, 2, 2, 3, 3, and 4, 4. I want to write with R8. R8 is empty set. Okay, start from the reflexive. Which one is reflexive? To talk about the reflexive, we need 1, 1, 2, 2, 3, 3, 4, 4, because this is set A. Look at the R1, 1, 1, 2, 2, 4, 4. Do we have a 3, 3? No, so reflexive is not. R1 is not reflexive. Now check about the R2. We have a 1, 1, but we do not have a 2, 2, and 3, 3, so R2 also is not reflexive. R3, 1, 1, 2, 2, 3, 3, 4, 4, yes. R4, 1, 1, 2, 2, 2, no. R5, 1, 1, 2, 2, 3, 3, 4, 4, yes. R6, no. R7, yes. R8, no. Do you have any question regarding the reflexive? Ali? Reflexive means, look at your set A. In a set we have a 1, 2, 3, 4. All element must be related with itself. Means 1, 1, 2, 2, 3, 3, 4, 4. If in a relation you have them, that is reflexive. If you don't have all of them, that is not reflexive. Next part is talking about the symmetric. What's the symmetric? Talk about the symmetric, you don't need to check the set A. Just look at your relation. I'm talking about the R1. Don't check the same number. For example, 1, 1, we don't need it. Look at the 1, 2. Do we have a 2, 1? Yes. Go to the next number. Next number is 3, 4. Do we have a 4, 3? No. Since we don't have it, right? It's not symmetric. R2. 1, 1, you don't need to check it. 1, 2. We have a 2, 1. Therefore, yes, it is. R3. We have a 1, 2 and 2, 1. We have a 1, 4, a 4, 1. Rest, done. You don't need to check them because we have a 2, 2, we have a 3, 3, 4, 4. You don't need to check them. R4. We have a 2, 1. Do we have a 1, 2? No. Stop. I said that it is not symmetric. R5. First element is 1, 1. Don't check them. 1, 2. Do we have a 2, 1? No. Stop. I write it. It's not symmetric. R6. We have a 3, 4, but we do not have a 4, 3. It's not. R7. Is that symmetric? 1, 1, we don't need to check it. 2, 2, we don't need to check it. 3, 3, we don't need to check. 4, 4, we don't need to check. Therefore, yes, we do not have any problem. R8. We have no problem. So here I want to put in some note. To be a reflexive, all of them must have a loop in a graph. If you do it, if you draw the graph, you will see that all of them have a loop if it's reflexive. About the symmetric, if you saw one directed arrow differently, that is not symmetric. Draw the graph of all of them, you will see it. The next part is talking about antisymmetric. Antisymmetric said that if you have any element we don't want to see its opposite one, don't check same thing again. 1, 1, don't check it. 1, 2. Do we have a 2, 1? Yes. Stop and say that, okay, this is not antisymmetric. Look at R2. 1, 1, don't check it. 1, 2. Do we have a 2, 1? Yes. This is not antisymmetric. Go to the next one. 1, 1, don't check it. 1, 2. We have a 2, 1. Stop. It's not antisymmetric. Go to the R4. 2, 1. Do we have a 1, 2? No. Up to here is fine. Go to the next number. 3, 1. Do we have a 1, 3? No. 3, 2. Do we have a 2, 3? No. Go to the next number. 4, 1. Do we have a 1, 4? No. Up to here it goes really good. 4, 1. We do not have a 1, 4. 4, 2. We do not have a 2, 4. 4, 3. We do not have a 3, 4. So it's yes, it's antisymmetric. Go to the R5. 1, 1, don't check it. 1, 2, do we have a 2, 1? No. 1, 3, do we have a 3, 1? No. 1, 4, do we have a 4, 1? No. 2, 2, don't check it. 2, 3, do we have a 3, 2? No. 2, 4, do we have a 4, 2? Still no. 3, 3, don't check it. 3, 4, do we have a 4, 3? No. Therefore, yes, that one also is antisymmetric. Go to R6. 3, 4, do we have a 3, 4. Do we have a 4, 3? No. Good. That is antisymmetric. About the R7. 1, 1. Don't check it. 2, 2. Don't check it. 3, 3. Don't check it. 4, 4. Don't check it. So that one is antisymmetric. And R8, that one also is antisymmetric. If you have a problem about the antisymmetric on a set, draw the graph of these relation. In a relation, if you saw both-sided arrow, definitely that is not antisymmetric. And last part is talking about the transitive. Talking about the transitive is a little hard. Hard, I mean, it's needed a time. Pay attention, I want to write it. If you have a B and BC, then we need AC. If you have it then check AC. Pay attention, these two must be same. Okay. You don't need to pick up the same numbers again. So first one is 1, 2, 2, 1. Answer is 1, 1. We have it. Pay attention, I'm not checking the same numbers. I'm not checking same numbers. You don't need to check them. So 1, 2, 2, 1. We have a 1, 1. Okay. Now 2, 1, 1, 2. Answer is 2, 2. We have them. Go to the next number. 3, 4, 4, 1. Answer is 3, 1. Do we have them? No. Therefore, that is not transitive. R2. 1, 2, 2, 1. Answer is 1, 1. We have them. What about if you pick up 2, 1 first, and second one is 1, 2, like this one. 2, 1, and 1, 2. Answer is 2, 2. Do we have them? No. Therefore, this is not transitive. About to the R3. I don't want to pick up 1, 1, 2, 2, 3, 3, 4, 4. Don't check them. One, 2, 2, 1. Answer is 1, 1. We have them. 2, 1, 1, 2 is 2, 2. We have them. 1, 4, 4, 1. We have them. 4, 1, 1, 4. We have them. Yes, this is yes. R4. Let me check it. If you pick up 3, 2 at first, and 3, 2 at first, 2, 1 at the second, answer will be 3, 1. Look at it. I want to write it. 3, 2, and 2, 1. Answer is 3, 1. Do we have it? No. Therefore, write it. It's not. But if its work is not meaning that that's transitive, you have to try to see that for all possible. Next number is R5. Don't check the same numbers. Yes, R4. Thank you, Ali. Thank you, Ali. So let me. I had a mistake. Thank you for correct me. So let me check it again. So I'm talking about the R4. We have a 2, 1. Okay. 3, 1. Okay. 3, 2 is 2, 1. We have it. 4, 1. We don't need to check it. 4, 2, 2, 1. 4, 2. 4, 3. 3, 2. Is 4, 2? Yes, this is transitive. Thank you, Ali. Really. So R4 is transitive. About the R1, R5. 1, 2, 2, 3 is 1, 3. We have them. 1, 3, 3, 4 is 1, 4. 1, 4. You don't need to check it. 2, 3, 3, 4 is 2, 4. 2, 4, 4, 4 is, yes, the other one is also transitive. What do you think about the R6? Is that transitive? Answer is yes. Because condition for transitive said that if we have A, B, and B, C, then check it. But since we do not have that much information, we said that okay, R6 is fine. R7. Don't check the same numbers. Therefore, do we have any different numbers in R7? No. The answer is transitive. R8 also is transitive. So we learn about the reflexive, symmetric, and symmetric and transitive. Next part is said that equivalence relation. What's equivalence relation? Equivalence relation is a relation which is reflexive, symmetric, and transitive. Let me write it. If it's reflexive, plus symmetric plus transitive. We call it equivalence relation. Equivalence relation. Now, R1, is that equivalence relation? Answer is yes, because reflexive, answer is no, because all of them must be reflexive, symmetric, and transitive. So R1 is no, R2 is no, R3 is yes, no, no, R6 is no, R7 is yes, R8 is no. The other one is partial ordering. Partial ordering or partial order. If it's reflexive, antisymmetric, and transitive. Reflexive, antisymmetric, transitive. We call it partial ordering. Partial. Okay, first one is no, R1 is no, R2 is no, R3 is no, R4 is no, R5 is yes, R6 no, R7 yes, R8 no. These are all topic for today. Some student has a problem talking about the symmetric and antisymmetric. They said that if it's symmetric, means it's not antisymmetric. If it's not symmetric, therefore this is symmetric. That is not correct. Look at it. In R1 is not symmetric and also is not antisymmetric. R7 and R8, both of them at the same time are symmetric and also antisymmetric. Can you see? So it's not true that said that if it's symmetric, impossible to be antisymmetric, or if it's not symmetric, definitely that is antisymmetric. This is not the true case. So let us continue. Look at these, doing these exercises at home to see that which one is equivalence relation and which one is partial ordering. In general, just check reflexive, symmetric, antisymmetric, and transitive. Later on, you will decide about which one is equivalence relation and which one is partial ordering. We know that at the end, relation is a one set. Even you can do this combining the sets, means combining the relation, means you can do the union, you can do the intersection, you can do any operator that you want, you can play on them. Let us say that R1 is a relation on a set K, R2 is a relation on a set B. Since R1 and R2, we know that they are relation, but at the end they are set. You can find union, you can find intersection, and you can do any operator between them if you want. And next example talking about, we have a two relation. Both of them are defined on a set of real numbers. Relation R1, all pairs x and y such that x is less than y. R2 is a relation which x is greater than y. Now, what do you think about the union? R1 said that all x less than y, R2 said that all x greater than y. So R1 union R2 is a set of all x and y such that x is less than y or x is greater than y. In the other word, we can say that x is not equal y. X is not equal y means x less than y or x greater than y. Intersection. Do we have intersection? No. R1 minus R2. R1 minus R2 means all element in R which they are not in R2. Do we have any element in R1 which is not in R2? All of the elements in R1 are not in R2 because intersection is empty. Therefore, R1 minus R2 is R1. Same thing for R2 minus R1 is R2. Now, hardest part. XOR. We know that R1 O plus R2 is R1 minus R2 union R2 minus R1. We found that R1 minus R2, this is R1. R2 minus R1, this is R2. So R1 O plus R2 in this example is same as R1 union R2. That we found it here, so it's same thing. So R1 O plus R2 is same as R1 union R2 in this example. All of them written in this solution part. Let us find the composite relation. What's a composite relation? If you have a two relation, R is defined from set A goes to set B. So R is here like A, B. And relation S means B goes to C, means B, C. Composite of these two relation means from A to C. Means these two will be AC. You cannot write it AC. Try to write it, but it's not work. Oh, I did write it. My pen start to make a problem. It's not writing anymore. Anyway, we call it composite relation, SOR. Let us have an example. Okay, it's writing now. Let's give an example about it at first. I want to give an example from the high school. If you have a one function f of x is equal to 3x plus 2. And we have one another function g of x is x minus 4, for example. How much is f of 1? 5. How much is g of, for example, 5? 1. Just put some numbers. I want to just put some numbers. Here I can show these numbers in this way as well. I can write it in this way, 1 and 5, 2 and 8. I can write 3 and 11. Means first numbers are input, second are output. I can write for g as well, 1 and 5, 2 and minus 2, 3 and minus 1. These are just showing as an element of input and output. I'm thinking about how much is f inside g of, for example, 1. So put 1 into the g, answer become as 5. Put 5 into the f and calculate it. Let me write it f of 5 here as well to see it. We call it FOG. We call it, this one is FOG at the point 1. So FOG means inside of f there is a one another function, its name is g. If you don't know this function, You can play with this way. Look at it. If you having 1, 5, we have a 1 and 5. And also we have 5 and 17. This is in function g, this is in function f. How much is f g of 1? Look at it here. That is 1 and 17. Means 1 and 5. Write 1. Put 5 in the function f. Answer is 17. We call it composite relation. Composite relation. The same thing like a composite function that you know it in high school. Composite function is a special case of the composite relation. So let us erase these items and to show you some examples. Assume we have a two relation, something like a two functions. R is a one relation, S is a one another relation. So first numbers are input, second ones are output. We want to check, do we have a SOR? Do we have a ROS? Let's start from SOR. Since R is written here, write the one pair. Let's start from R. From R, pick up first one. Write first input and use second input. Where we have to put it? We have to put it in S. If one we put it in S means this one. Input is 1, output is 0. Use 0. Go to the next number. Next one is, again, go to the R. We always start from R. Pick out 1 and 4. First element, write it. Second element, put it in 4, in S. If you put in S, we have a 4 and 1. Write 1. Go to the next number. In R, we have a 2, 3. We have a 2, 3. Write 2. Put 3 in S. If you want to put 3 in S, we have a two possibility. Maybe output is 1, maybe output is 3. So duplicate in one of the possibility, write 1, in the other one, write 2. Next number is 3 and 1. Write 3, put 1 in S, the answer becomes 0. And last one is 3 and 4. Write 3, put 4 in S, answer becomes 1. This is SOR. Now think about the ROS. Let's start from S. Pick up first number, 1 and 0. Write 1, put 0 in R. Can we put 0 in R? None of the input is 0. Look at them, none of them is 0. Means this ROS is not defined. We have it just SOR.